Welcome back. We will have lecture 9 for the course corrosion failures and analysis, and we will continue our discussion on galvanic corrosion. So, the course is and topic galvanic corrosion. Now, if we see that in case of galvanic corrosion, it basically is defined as two metal corrosion, and one example we have provided is iron and zinc case. And we have seen couple of observations. The observations were preferential cathode and anode, and second observation was cathode also corrodes, but very small corrosion rate, and anode corrodes at a high rate. Fine. And interestingly, one more observation we can make out of it. If we see that zinc and iron situation, the cathodic reaction is nothing but H2, and anodic reaction was plus. Of course, its corrosion rate is very small, its corrosion rate is very high, but it does not stop. Now, interestingly, if we consider a situation like what we had in case of Daniell cell, that we have one end copper is dipped in copper sulphate and copper ion activity was maintained at 1, and another end we had zinc and zinc activity, and it was dipped in zinc sulphate, and activity of zinc ion was maintained at 1, and we developed some potential, and that potential we measured by standard hydrogen electrode, and here also we also maintain standard hydrogen electrode, and then we measure the potential. Now, interestingly, this potential, if we maintain this condition, it is coming out to be 0.34 volt, and here it will be minus 0.76 volt. Now, this potential, how it is coming? From Nernst equation. Considering this reaction, and every time we are considering reduction potential, that is what I have written in terms of reduction. where the reaction was zinc. Interestingly, this would become, if we connect them, and remember that should be a Scholl bridge to maintain electrical connectivity, and here we connect this with a conductor with a, and then current will flow from this copper into zinc, and this is positive or cathode, and here it is negative or anode. Now, if you see cathodic and anodic reactions, the same ion is depositing and same metal is forming the ion. In case of zinc surface, it is zinc which is going to the anodic situation when it is connected. So, that means preferentially anodic reaction would happen here and preferentially cathodic reaction would happen here. And interestingly, here since we are not having any other species other than copper plus plus, only this cathodic reaction can take place and only this anodic reaction can take place. This is corrosion and this is deposition. Since copper has a higher reduction potential, that is what it actually reduction process is preferred here. Now, this case and this case is different. So, this is also galvanic corrosion of zinc, but here we have ions of both the metals in the solution. But in this case, ion of iron is not present, iron of zinc, ions of zinc is also not present in the solution. Initially, to start with, it was only H plus, but still we ended up getting this reactions. So, that is another important aspects, because these things are coming that because this value is this and this is nothing but which is standard reduction potential of zinc. But in practical cases, we experience the situation what we had in case of iron zinc. Ions of individual metals may not be present in the actual situation or practical situation. So, that time we cannot judge that which type of reaction would happen from the reduction potential. For example, here we cannot judge from the iron reduction potential, which is minus 0.44, the standard reduction potential for iron, and zinc it was minus 0.76 volt standard reduction potential, because those ions are not present in the solution. So, in this case it is very easy how to decide anodes and cathodes. For example, if we have two metals M1 and another case M2, and they are in their respective ions in connection with respective ions of that electrolyte where we have that respective ions. This is M1 N plus and it is M2 N plus, both the ions are present in those electrolyte. So, I can decide which will act as cathode and which will act as anode if the such situation arises, simply by looking at the Nernst equation, which is generalized form this is the generalized form we can use, and we know that there is a series exist. For example, here if this value is greater than, so then M1 would be anode, M2 would be cathode. Okay, and the reactions would be in this case and in this case M2. So, these will be two reactions. that way we can judge. So, in so pure cases, so it can be possible when it is a pure case, pure species, and here we can judge by looking at standard reduction potential series. And that series, for example, if I try to point out, here you will get like this AU, AU 3 plus, E 0 value would be 1.498 volt, and this is all with respect to standard hydrogen electrode. This is gold. Two plus is basically like that way. You can go up to magnesium. So, like that way we can have a series which is based on finding this value by putting the same ion of that particular metal, maintaining that ion concentration to be activity to be 1. So, for example, here if this concentration is 1, this activity is 1, then of course, potential of that particular electrode would be same as reduction potential, standard reduction potential, because this ln part would be 0 if the activity of metal ion concentration is 1. So, like that way we can find out these values. And here if I try to see this, if we connect it to this too, when their ions are present, then this would be cathode and this would be anode. Similarly, if I connect magnesium with nickel, this should be cathode, magnesium would be anode. Similarly, if I connect nickel with copper, nickel would be anode, copper would be cathode. Fine. It is very easy to find out, but it is impossible to get in practical situations. So, that time we have to generate another series that is called galvanic series. Galvanic series, and in that galvanic series we have to just find out that which one in a two metal contact, those two metals could be alloy, those could be metal could be pure metal, those could be pure metal and alloy, all those combinations are possible. Even it could be same metal, but the reactions would have different activity. Okay? I will come to that. So, galvanic series how, and it starts with this particular discussion that cathodic reaction and anodic reaction, if you see, cathodic reaction is always this, even if iron remains cathode, Why we say this? Because cathodic reaction, wherever cathodic reaction happens, it is basically cathode, but that does not mean that that particular metal will have a cathodic reaction. Here it is not happening, rather that cathode is actually going through anodic reactions. So, that is what we need to have, a kind of comparative series which will not get bound by the values what we have in standard reduction potential series. And these series could be different for different electrolyte. Let us say how we find that series. Okay. So, let us say we have a metal 1 M1 and M2 and another metal M3. Let us say all are M1, this M1 and metal, M1 metal and M2 metal, they are dipped in, let us say NaCl solution or seawater solution. This is M1, this is M2 and let us say this is aerated solution. And if we connect them, this is a salt bridge, SB is nothing but the salt bridge. Now, we have to just check which way current moves. If current moves from this end to this end, so the current flows from this end to this end, and we know that in galvanic connections current always moves from positive end to negative end. So, this will be cathode and this would be anode. So, this is anode and this would be cathode, since this is a galvanic mode of situation and here the corrosion is taking place. So, that case M2 would corrode and M1 would act as, this is anode, M1 would be the surface for cathode or cathodic reaction cathode. And interestingly, when we have this NaCl, there we did not have Mn plus, here also we did not have M2N plus. So, that way we can see that by looking at the current flow, we can check which one is active, which one is less active. So, the less active metal in this series in NaCl solution, whatever 3.5% of seawater, in this series M1 would move on top of M2, and here we are not putting any values. You can also find out the values here by joining standard hydrogen electrode, you will get some potential, but we are not mentioning that, we are just comparative. We are making a comparative statements that we are actually which one is acting as a positive end, which one is acting as a negative end. So, accordingly we decide which one is cathode and which one is anode. Similarly, if we have a joining like a condition like the same condition, instead of M1, if we put M1 and M2, let us say when we join this like this same situation what we have here, if the current moves from M1 to M2 in the external circuit, then definitely M2 is cathode and M1 is anode. So, that means we can see that if we compare M3, if we compare M1 and M3, definitely M3 is less active and M1 is more active. So, more active one dissolves and less active metal will act as cathode where cathodic reaction happens, and here. So, that means M3 would stay on top of M1. So, now we have a series which is M3, M1 and M2. So, if we join then M3 and M2, definitely this would be positive, this will be negative. Now, interestingly, what are the cathodic and anodic reactions? Since I have said that this is aerated, so we have dissolved oxygen, and if we consider NaCl solution, it is a neutral solution. So, the cathodic reaction would be an anodic reaction M1 minus Ne equal to M1 N plus, sorry, it should be M2, okay. Even if it is M1, no problem. In that case, this is joined M1 and M3, because M3 is acting like cathode, and another anodic reaction would be M2 minus 2E equal to Ne. So, let us make a generalized statement, n number of electrons are associated. So, it would be M2 n plus, that time M1 and M2. So, in this case this is positive, this is negative, in this case this is positive, this is negative, and that is what it is followed in that galvanic series. So, now in the galvanic series this M1, M2 and M3 could be metals, could be alloys, and could be some reactions also, okay, fine. Now, but if we consider only metals, so we can have a series like this, in let us say sea water. And interestingly, before I get to that particular thing, so that means you could see that if you change this NaCl solution, you can change it to some other solution, you might find that M3 might become active compared to M1. So, it is not sacrosanct that in one particular electrolyte one metal or alloy is less active or noble, does not mean that that will remain noble in other solution. Okay. So, in order to understand the industrial applicability of galvanic series, we have to see a complete galvanic series and see how we select materials in order to prevent corrosion related problems. And whenever we select materials, we try to select materials which are close by in the galvanic series in that particular environment. Okay. So, in order to understand that, we will take this galvanic series discussion, because it involves a lot of engineering applicability in the next class, because this particular class we have I think hardly left with 10 minutes. So, 10 minutes will not be sufficient to understand this galvanic series situation, but at least I could tell you that what is the implications of galvanic series and standard reduction potential series, because in case of standard reduction potential series we always deal with same metal, same species and unit activity is maintained, but in case of galvanic series it is not needed. So, for example, if we consider steel and stainless steel, fine. So, let us say you have a stainless steel SS and 304 standard form of 188 austenitic stainless steel. Austenitic stainless steel, and in this case if we have another steel which is mild steel, and you let us say you have made an electrical contact. So, you have one is mild steel, another one is stainless steel, and if this couple if we expose to normal potable water, you would see that the SS would become cathode, hardly any corrosion will be noticed there, and but this will be highly corroded. Okay. Why this situation happens? Because if we compare the galvanic series in potable water, SS would always stay on top of mild steel, and their difference in potential, even if you measure the potential in the potable water, this difference in potential is large, and in fact when you connect them, the large current will flow from SS to the mild steel from the through the conductor or to the external circuit, and here the conductor is nothing but this, and this is the electrolyte. So, here ions move and here electron moves. Okay. So, SS would become cathode and MS
image becomes anode. But here interestingly they are not pure metals, they are highly, the SS is highly alloyed metal and MS is less alloyed metal, fine. So, this is very important because this tells me that we cannot have such kind of situation where highly noble and highly active metals cannot be joined for an engineering applications. Okay. So, we have to be very careful that part, that we have to select materials so that their galvanic series, in the galvanic series they are close by, but in this case they are wide apart. So, wide apart means it will be highly cathode and highly anode, okay. And if it is they are close by, the galvanic effect will be hardly noticed. Okay. So, we will talk this part in our next lecture. So, till then let us stop here, we will continue our discussion on galvanic series as well as galvanic corrosion, because this galvanic corrosion I consider to be one of the fundamental corrosion forms. Thank you.